Hello everyone. In today's video, let's work on a problem related to number sequence. Here comes a question. Your number sequence En, the recurrence expression is an plus 2 equals an plus 1 squared plus 2 to the power of n plus 2 over an. A1 equals square root of 2 and A2 equals 2. Find a closed form expression for an. This recursive expression is composed of fraction, square, and the exponent term. The first thing that I'm going to do is to eliminate this exponent term 2 to the power of n plus 2 to make the formula more simple. To achieve that, both sides of this equation is multiplied by an so that the fraction part is eliminated. Then, both sides are divided by to the power of n plus 1. So then, this exponent term becomes a constant term. An plus 1 squared over 2 to the power of n plus 1 can be written as an plus 1 over square root of 2 to the power of n plus 1, then squared. Here, I'm going to define a new number sequence Bn, and Bn plus 1 equals an plus 1 over the square root of 2 to the power of n plus 1. Of course, on the left side of the equation, I'm going to do a similar change by separating 2 to the power of n plus 1 into two parts. Then we can find out the left side is actually equal to Bn times Bn plus 2. Then the entire expression can be written as Bn plus 2 times Bn equals Bn plus 1 squared plus 2. Up to now, we have successfully changed the original recursive expression into a new one in which the exponent term is eliminated. It looks simpler. And here, don't forget to calculate the values of B1 and B2 according to A1 and A2. This is fairly simple. B1 equals 1 and B2 equals 1, 2. In this new recursive expression, I'm still not happy about this constant term. So my next step is to remove this constant term. To do so, I'm going to rewrite this equation by changing n to n minus 1. So it becomes Bn plus 1 times Bn minus 1 equals Bn squared plus 2. The first equation is separated by the second one and get Bn plus 2 times Bn minus Bn plus 1 times Bn minus 1 equals Bn plus 1 squared minus Bn squared. Here, we have successfully eliminated this constant term too. As the next step, I'm going to move the ones that contain common factors to the same side of this equation. This is how it looks like. Then, this common factor can be taken on both sides. So the equation becomes Bn plus 2 plus Bn times Bn equals Bn plus 1 plus Bn minus 1 times Bn plus 1. Then both sides of this equation can be divided by Bn times Bn minus 1 so that it becomes Bn plus 2 plus Bn over Bn plus 1 equals Bn plus 1 plus Bn minus 1 over Bn. Note that the left side and right side of this equation has very similar formats. The only difference is in the place of n plus 1, it changes to n becomes the right side of this equation. That means such equal relationship can be passed down up to b3 plus b1 over b2. We already know that b1 and b2 equals 1, and easy to find out that b3 equals to 3. Then the entire expression is equal to 4. That means bn plus 2 minus 4bn plus 1 plus bn equals 0. Now we got a new recursive relationship of bn. In this new recursive equation of bn, bn plus 2 is a linear combination of bn plus 1 and bn. This type of number sequence is called constant recursive sequence or linear recurrence sequence, such as the Fibonacci sequence. Solving this type of sequence has a standard way. If you already know how to do so, you can skip this part. Otherwise, the first thing that we need to do is to find out the characteristic equation of this number sequence, which is lambda squared minus 4 lambda plus 1 equals 0. Note that the coefficient is equal to the coefficients of this recursive formula. The two roots of this formula are 2 plus minus the square root of 3. Then, the closed form expression of Bn can be written as alpha times lambda 1 to the nth power plus beta times lambda 2 to the nth power. Here, alpha and beta are two unknowns that we need to solve. To find out the values of alpha and beta, we just need to let n be 1 and 2. If n is 1, from b1 equals 1, we can get one equation about alpha and beta. If n equals 2, from b2 equals 1, we can get another equation about alpha and beta. And solving those system of equations, we can find out the values of alpha and beta. And then finally, we plug alpha and beta into the expression of Bn. And then from here, we can get the closed form expression of Bn. It's quite long here. And at the last step, An equals square root of 2 to the nth power times Bn. And then this is the final format of the closed form expression of An. Thank you.